Here's the sample test for chapter 3. In number 1, we have the oxygenated blood in equilibrium, and that's a very important point within non-oxygenated blood. And they have slightly different colors, and that's how those fingertip oxygen sensors, oxygen content sensors work. If you've ever had one on in the hospital or at the doctor's office, sometimes they just pop one on you just to take a check if you just even go in for an exam. And how those work are on YouTube, by the way. Anyway, so how do we know when the equilibrium in the body tissue has been established? Well, at equilibrium, each reaction is running the same amount. The dump of oxygen off the hemoglobin and the acceptance back onto the hemoglobin. So overall, there's no change. So when the color remains the same, then just as much is being dumped per second as accepted per second, and that's when you know you have equilibrium. Onto the key to understanding this, and they don't exactly say this, is that all these reactions will somehow add up and cancel out and so forth to make this. This is the overall reaction. So what I'm going to do to save myself time is not consider all these chemicals. I'm just going to grab one that looks unique and see where it places, like this. I'm going to say calcium carbonate is on the left and it's got a coefficient of 1. Oh, that's also true here. So this line must be unaltered. You can go through and do the rest, but you're wasting a lot of time, because if they were going to have to multiply this one by a certain number, then also those. You can't be different. So if this is remaining as its original coefficient, so are these, which means that the K is unaltered. So I didn't make any note there because I'm leaving it. The calcium hydroxide is on the left, the coefficient is 1. The calcium hydroxide is on the right of the arrows, and the coefficient is 1, which means I need to flip this one end to end, which means that when I take the KCs here and multiply them to get the overall KC of the overall reaction, what I'm going to do is multiply by the inverse of this number, which is what I did here. So it's on the bottom of the fraction. That's multiplying by the inverse, which is the same thing as dividing by it, right? On this one, I've got the bicarbonate ion, and it's a 1 on the left, but here it's a 1 on the right. So this one also needs to flip end to end, which again takes the Kc and multiplies it by the inverse, puts the inverse into the whole math equation here. So here it is on the bottom of my fraction. On this one, the water is a liquid, coefficient 1 on the left, and also in the overall. So I'm going to leave this one alone. So here I have number 1, number 4, number 2, number 3. And remember, because I flipped these end to end, I have to multiply by the inverse. If you don't know what I mean, go ask your teacher. But the products became the reactants became the products. So when I did the K math on this, everything flipped upside down, which gives you the inverse of the previous answer for the K for this step. And then this is very doable without a calculator, actually, because 1, of course, doesn't affect the numerical part. And so 9 divided by 6 is 1.5. And these actually cancel out. I can say -6 here cancels out -6 of this. So this gets -3. And the same kind of thing happens here. And what I have then is 10 to the -3 times 10 to the -3, which is 10 to the -6. On 3, we have our little equilibrium type reaction. Notice we have a liquid, which won't figure into any K or Q type math. Note to self. We have a K, so if it's at equilibrium, that's true, but we're asked, will it shift? You know, if this is the partial pressure, will it shift? And if that's the partial pressure that generates K, then no, it won't shift because K is already true. So the question is, when we use this, which is our current situation, and maybe it's at equilibrium, maybe it's not, what we're getting is Q, and is Q equal to K? When I use this, do I get K? So what I have is products over reactants, the power of the number in front, but this is a liquid, it's not a gas, so the denominator of that fraction I just said becomes essentially just 1. And I don't have anything else, so I'm going to get 0.8 to the power of 1, and so Q is just, boom, it's just 0.8. So is my current situation generating K? 1? No, it's not. It's generating a smaller number, which means that the numerator of my fraction, remember the denominator was just 1, the numerator is not big enough to reach K, which means that this system is going to shift in the correct direction so that K in this case gets bigger because Q is smaller than K. So this is going to shift to make more products until the proportion is correct that K is true. Now in this case, that's really easy to figure. They don't ask it, but we do know what will happen is that this will shift until this reaches 1 atmosphere, because then we'll have one atmosphere to the power of 1, and that will give us 1, and K will be true. 4 is a bit of a repeat of 3. We're being asked which way this would shift. Well, what molarities do we have? Well, we have a K here and 0.5 moles and then 1 liter. So that's really easy. We have 0.5 molarity in all 4 spots. They wouldn't have to do that, but this is supposed to be one of those problems that's really quick if you know what you're doing, if you're not having to review the concepts here. Also, they could have easily put a 2 liter, and then all my super math people might notice that if you have equal numbers of items here, terms in the numerator and denominator, that dividing by 2 or 3 or 29 in all cases would cancel out. But that would not be true if you had, say, 3 of them up top and only 2 on the bottom, or vice versa. It only works when you have the same number up top and on the bottom. So in this case, we could skip the liters no matter what it was, but not always. So if you're in a panic, just put the liters in on the bottom, divide by the liters. But in this case, of course, it's 1, so that makes it super easy. So the molarities are 0.5 in all cases, which of course just cancels out to 1. Q is 1. The K math at the moment gives us a 1, but what is K at equilibrium? It's 1.5. So we don't have enough. Q is not big enough to reach K, which means in our fraction here, we don't have enough numerator, which means we don't have enough product, and everything will shift to the right until the proportions are such that K is actually true. On 5, we have this fictional reaction, and so we start off with no product, so the product starts at 0 and rises, and the reaction starts at some amount. I think this graph is a little bit misaligned, and that it should be starting at 0.8. So that's where I think the tiny error is. If this starts at 0.8, then this makes a lot more sense, because we should be destroying 3 and creating 4. So if this rises from 0 to 0.8, and notice then it levels off, so we've got an equilibrium because the molarities are not changing out here. So that's the equilibrium state. We rose from 0 to 0.8, and this should fall 3/4 as much, because we're destroying 3/4 as much as we created. So if it went from 0.8 to 0.2, then I've destroyed 3/4 as much. So I think we got to draw a big dot there and mentally move that graph over. They wouldn't be so careless on the real test. So what would K be in that case? And I did it down here. Then you would have 0.8, because the equilibrium value here is 0.8 molarity, brackets is molarity, 0.8 to the 4th over 0.2 to the 3rd. And what you can say is each one of these cancels out to 4. This is this over that is 4, and you get that 3 times, and then one of the 0.8 remains, and then you don't really need a calculator. You can just do some 6th grade multiplying and get the K. And then I changed it up. What if for some reason this went out to 6, and I was 0.6, and I know some of you will say, well, that can't be 0.2 if that's 0.6. I know, not according to that reaction, but just as a bit of practice here, what would it be? And you would get 0.6 to the 4th over 0.2 to the 3rd, in which case this over that is 3, and we would cancel that out 3 times and get one remaining 0.6. And again, some 6th grade math would give you the Kc in that case. On number 6, we have our reaction, and we put in only reactant, no products. So it's going to start with a certain amount. It's going to start with 2 atmospheres and then proceed to the right. So there's no need to do Q or anything, because we know it's got to go to the right, because there was no product to begin with, so it couldn't possibly go to the left. Also notice that the solid won't matter in any kind of K math, and what we're looking for is K. Now for K, we have to have molarities of the reactant and the product, and so we're going to have to do some figuring here. We know we start out with or atmospheres in this case, excuse me, but we're starting off with 2 atmospheres, and we will destroy 2 of these to make 3 of those. So this will get destroyed in a 2/3 ratio of that, whatever X is. will destroy 2 and create 3. And so here's the amount at equilibrium. I just figured you couldn't read this, so I wrote it out. Here's my icebox in it. So here's my equilibrium amounts. So I have my equilibrium amounts, but really I have 2 unknowns because what I'm looking for is K, and I can't take these with X and put them into an equation and yet find K. That's 2 unknowns in one equation. So there must be a way to get out of this, and the way to get out is that we know that the partial pressures add up to the total pressure, and I do know the total pressure at equilibrium. So this value plus that value must add up to be the pressure total at equilibrium, and then I can solve for X. That is not good enough though, and I know some kids will stop right there and say, I found it, I'm done, and they'll say, somebody will put K equals 0.4, which is super wrong. K is not the value of anything in this equation, much less K. It's not even the value of one of the molarities, because the value of the F2 is 3 times whatever you just found it for X, isn't it? So the value of the F2 is 3 times that, and the value of PF3 is 2 minus double X. So that's the value in atmospheres of the PF3 at equilibrium. And then we can take those values and put them to the third power on top and to the second power on the bottom. But look, it's very neat and tidy. It all cancels out, or 2 of them do. 2 of these cancels out 2 of that, leaving 1 of these in the numerator. And you don't even need a calculator at all. And it just cancels right out and leaves you 1.2 for KP. On 7, we have this particle diagram in a box, and the test writers really like this, so get comfortable with this. We have our fictional reaction and the ratio of molecules at equilibrium. And it's just a ratio. It's just a ratio. So we could say that stands in for the molarity or the pressure or whatever. So let's count them up, and we count them up. What's Kp? Well, it's products over reactants to the power of the number in front, and we get 1/16. On 8, we have our little fictional equilibrium reaction, and it's brought to an equilibrium. Okay, and then the temperature is decreased and the concentration of Y increases. So by decreasing the temperature, the amount of Y went up. So the reaction has shifted to the right. What can we tell about this? Well, one of the things they would love you to tell them is something like K went up. How do we know K went up? Well, it shifted to the right, which is more products, which is the numerator in K or Q math, but K math, and therefore the current situation that it was at, which would give us Q, is not high enough. If K slides up, then Q is currently smaller than K, and to achieve K, it has to slide to the right and provide more products. Also, it can pretty well be determined that this must be exothermic, because when you dropped the heat, right, you destroyed a bit of the right side's ability to make the left. So this is now the strong side, this is the weak side, and what we're dealing with here is Le Chatelier's principle. And by dropping the heat, we've reduced something on the right, and remember, Le Chatelier's principle says the system at equilibrium, which this is, will shift to relieve the stress. It will shift to the weak side, which would be the right side in that case. On 9, we have a sort of overall review of the idea of Le Chatelier's principle. How could we increase the production of this? Well, we could decrease the amount of O2, anything on the right, because we just said in number 8 that the system will shift toward the weak side. So we can make this weaker, or we can make this stronger, which means put in some of this, or increase the temperature. Also, though, there is something else that's kind of easy to forget, which is the pressure/volume idea. And what we need to do then is count the molecules of gas on each side. And this is 1 + 2 is 3. And remember, that's a liquid. So the gas molecules on the right side is 2. So it's 3 versus 2. And we want it to shift to the right so that we can produce more of this. So what we would do is decrease the volume, because that favors the side. We're decreasing the volume of the vessel. That would favor the side with fewer gas molecules, which is the right side, which is what we wanted. So we could decrease the volume, and that will increase the pressure, or I would tend to say it, or increase the pressure. I'm not sure how you would do that without decreasing the volume, but sure, you can decrease the volume or increase the pressure also.